Hello, Amiga coders. This is Photon, and I thought we'd continue and convert our demo to Dual Playfield mode. But first, we need to upgrade our source. I've done some things behind the scenes, meanwhile, and you may have noticed I made a few small changes to my startup routine that we put our demo inside to make it system friendly. And so if you assemble it, you will get this error. And if you look at the updated archive on Coppershade, uh, then you will find that I have put the latest version there. So that's what you do, and we'll assemble. The next thing is to upgrade your P61 player. Uh, there are very few changes. Most of the changes are ease of use. So it's simpler than ever to incorporate your P61 player into your demo. And the same thing there. The archive, the source archive on coppershade.org is updated to match. Now, I got a comment about some coders not being able to run the source. Uh, Depending on your assembler of choice, you may run into, you shouldn't have any problems assembling instructions like these, because they're standard. Mostly you will get into trouble when it comes to directives, such as include, uh, declare data, and things like that. So I think there aren't that many dialect differences between the assemblers. But one of them is this BLK, which is still in the source because I started out with ASM1 and sort of learned this way, and I think it's easy to read. Read that out as a block. But this is what you do to hopefully fix the source. Some assemblers will not have the even and odd commands. They will have CNOP commands. I think I went through that in an earlier tutorial. If you get into trouble, just leave a comment and I'll try to source any slight dialect differences between assemblers and get back to you with a reply. So mostly if the difference is to devpack, probably the only offending directive is the BLK command. So replace that with DCB and you're good to go. Global to replace all the occurrences. So DCB stands for declare block and works exactly the same way. So you should have no trouble there. Next up is if you have trouble, apart from choosing an assembler, the easiest way to follow this series is to use ASM1, ASM Pro, or ASM2. I recommend ASM2 because it's my daily driver. It's based on an early version of ASM1, which means that you will not be tempted to use instructions that are not for the CPU you're using, either in emulation or on your real Amiga, since these are OCS tutorials for mainly Amiga 500 and such nice machines. So I recommend to get ASM2, and you may see some features demonstrated in this tutorial. Let's get started. Um, One other feature that ASM2 has is that most of the work has been done on compatibility. Uh, ASM1 early versions do not always work on all rigs. The same is true for ASM Pro. It all depends on what kind of accelerator you got in your machine. Mostly it's accelerators that cause trouble, and if you have an Amiga 500, you should be able to run most early assemblers without trouble. The later assemblers may require things like Kickstart 3.1 and some libraries and some stuff like that. So that's directives. Maybe I should dig into that a little bit more. Directives are not instructions for the CPU, it's instructions for the assembler to compile your set of instructions and data into the executable program. So here's a directive called macro, and that declares this macro, which in turn contains uh, a compiler directive to insert this data into your source. At the bottom, we got things like include binary and things of this sort. You also have these section commands, which divide your executable into parts that the operating system will handle and put in the right place. So this section is the BSS section, which means that it will not add to the size of your executable. At runtime, when the executable starts, the operating system will reserve this many bytes for your data, and this is a good place to have buffers and things like that. Enough of that. I wanted to move on to Dual Playfield right away. So I will get oriented with my source. I might mention one other thing, and that is case sensitivity. So for example, this is a label, and this is actually the label in the source where the data is that you're pointing to. So can you see the difference? Capital C. So the capital C causes trouble if I just enable, hang on, if I disable this case insensitivity, then it will stop, should stop on that label. Yeah, so it doesn't know this label. If we change that, it will accept it. So likewise, this was a lowercase, I betcha, and so on. So if you are particular and you want your labels to be camel case, so-called, then by all means enable this option, the case sensitivity option. I'm just explaining why your assembler might stop on some lines, and that is because the case doesn't match. Your assembler should have an option to turn it off if you just want to get it running. So to convert this demo, let's see where we were first of all. So we got the Sprite Playfield, the Sprite Starfield, getting ahead of myself here, behind everything, behind almost everything, and we've got the copper bar moving in front of and in back of the logo. Let's see how that works for us with Dual Playfield Mode later on. So luckily I've planned ahead. So with this in mind long ago, I decided to not use more than 8 colors, or to be exact, 7 colors. And this enables us to add another layer. We can put this layer behind or in front of the other playfield and or the sprites. So you can determine the order. I will put it in front of the logo, in front of everything except the scroll text. So the way to do this is to just go through the copper and see what you need to change. So this takes us back to the modulos. Currently we have a bitmap display. You could see this as one big playfield. It's a single playfield mode in which the odd and the even bit planes modulo must be set because we are using the odd and even modulos for up to 6-bit planes. We're just using 3 though, so what is needed for dual playfield mode is to interleave or use the odd bit planes for one playfield and the even bit planes for another playfield. This also affects the palette, which we will see later. It does not affect palette color number mapping. So from top to bottom, we may have to change this. We don't know yet. We will have to change the bitplane pointers because now we're using bitplane pointer 1, 2, and 3. We want to use 1, 3, and 5 for what we got now, and 2, 4, and 6 for the playfield that we'll add. So also we must set this to 6-bit planes because we will use 3 plus 3-bit planes, 3-bit planes in each playfield, and enable the dual playfield mode. We'll also need to set some colors for the other playfield and some other bits and bobs. Let's see how it goes. So let's start with the bitplane pointers. So we need 3 more bitplane pointers, and we'll need to move this up so that this is now bitplane 3. Copy that, swap that, oops. And that's our setup for playfield 1. Now we need to modify these, so we'll just use bitplane 2 to start with. And that's our bitplane ordering for the playfields. So we do set some colors. All of them are color 0 through 7, which means, well, color 0 is the background color. 1 through 7 is the colors we want for everything on the screen, basically, at the moment. So the new colors will be mapped to these bit planes. So first we need to change this to 6-bit planes and then add the bit for dual playfield mode. This is done. So to copy this and set the colors, we do this. Let me go through that. So we just copied the colors from playfield 1 to playfield 2, and this color, color 8, now has no meaning. If we had used 4-bit planes in normal bitmap mode, it would have been color 8, but at the moment it serves no purpose, so let's remove that. The sprite colors start up here. Sorry, start at color 17, 18, and 19, so they won't have to be remapped or anything like that. So we got the color set up, we got the mode set up, and we got the bitplane pointers. We've inserted some bitplane pointers into the copper, which we will need to poke with the correct addresses to point to the new playfield. Next up is to check any other changes to the playfield, to the bitplane control, and generally see where the vertical stops are. Okay, here's something. We turn off all the bitplanes here to save some memory, actually. So this is below the logo, right? So we turn off the bit planes there to not have to declare more empty memory below the logo in the memory. So if we remove this, I can actually just snip that out and that. Now that we don't disable the bit planes here, Denise will continue to read from chip memory and basically display whatever garbage is in memory below the logo. So we'll have to have a look out for that. So this font palette should not affect anything because we set the bitplane pointers to use the first 8 colors for the scroller as well. We will have to likewise change this to just use odd bitplanes 1, 3, and 5. So that's how you do that. We'll also have to look out for any modulo changes. So what we want to do here is set. We no longer want to set the even bitplanes modulo for the new playfield necessarily to the same value as the existing playfield, right? So if I remove this, likewise, Denise will continue to read bitplane data for the other playfield from memory, chip memory, until we say otherwise. Also, I would not like to change the mode, so please remove that. This was previously set to 3 bit planes as well. This will no longer be used, so if you reduce or have reduced the number of bit planes in the font, you will have to adjust this. Because normally you'd then, for 3 bit planes, you'd have 3 in the front, 3 in the back, equaling 6 and turning on Dual Playfield mode. But if you reduced the number of bit planes anywhere, you might use this. This would not, I don't think this would work if you're using a 1 bit plane font. Let's assume that you're using a 3 bit plane font, and we're going to use all the maximum number of bit planes that the OCS Amiga supports. So the 6-bit plane Dual Playfield mode continues here. Anything else to look out for? These are just color changes for the floor. This stop makes sure that the display continues beyond line 256 for PAL displays, and some more color changes. We want to remove this as well, and that should basically be it. The change I've yet to make is the very first modulo setting, because I haven't decided on that yet. For now, I will set it to the same width as the logo, which was 320, which is plenty. But I don't want to reuse these. If I leave these symbols as they are, then when I want to change something, it might not be correct. I want to declare a completely new buffer with its own settings that I can change whenever I want. So I'm going to call the new buffer sky. So this symbol will be sky byte width, and this symbol will be sky bitplane count. It's a byte count for each bitplane. The number of bytes for 1 bitplane of 1 line in the new buffer. 1 pixel line in the new buffer. Very detailed explanation. So what remains now, this should work. I'm going to save this because it's always tricky to, make a major change like we're doing now to an existing working source. So I'm going to save that as this tutorial and update it later. And I'm going to check where I want my buffer. I plan to put dynamic content in this buffer, so I'm going to treat it as a buffer rather than including some graphics. If you want to include some graphics, you can by all means put it after the logo here, but I'm going to declare it as declare space so that I can make it not make the executable bigger. I like to put labels to signify the end of buffers and things like that, as you can see here. That gives me an idea of how big things are, and it will also help me, it will make it easier to clear areas. And I want to clear this new screen that I shall call sky, because it will be the sky in front of the logo, and I will declare sky end, and I will declare it as sky byte width times the height of the complete screen, the whole demo screen, not just the height of the logo. So just copying this would have been wrong because I want to make the new play field cover the whole screen. So this H symbol is declared here. So we got a height of 256, and we're going to copy these values and rename them sky and make them the same as the logo. 320 by well, 320 wide. So these are handy values, as I explained before, for easily setting modulos. And actually, I want to just set this like this logo BPL logo byte width, because if I need to change them, I don't want them to depend on any values set in the logo here. So then I'll just declare a similar chunk of symbols and rename them sky. So that's our symbols and screen setup, and we've declared this buffer here. Now we need to poke the bitplane pointers. Here they are. This should still work because we're poking these values here, and we've only changed the custom chip register addresses that we put those values in. And these will be blank, obviously, if we start the demo now. We could try that. Should be displaying some garbage, maybe. Let's see. Yeah, so that's the 0 page of the chip memory displaying as a second playfield. And as you can see, when the copper bar crosses any data that's in the other playfield, you will notice that the copper bar is always behind. And there's nothing you can do about that because we're using the background color to make the copper bar, which means obviously anything is in front. Anything is in front of the background color. So to have the copper bar in front of the second playfield means that you will have to do it in some other fashion simply than using the background color to make the copper bar. So enough about that. We're going to see what pokes the bitplane pointers. So we have a loop here that pokes the bitplane pointers, and we're going to call this playfield 1 pointers. Copy that. Actually, copy that. And point it to the new buffer. And not reset the poke pointer into the copper list, but just continue poking. This requires that you don't put anything in between here, but it's rather unlikely that we would start inserting copper pokes in between here. So here's where we were. This playfield will now point to the sky buffer. And we also need to change this new symbol that we made in case we change it later. So instead of the 0 page, now we've got a double symbol, so just rename that. This is tricky. This is devious. Sometimes you forget to rename the jump pointer to the same as the label when you make a copy, and then you have an infinite loop on your hands. So now the demo will display some other garbage than the 0 page garbage, or the assembler might clear the buffer we declared for us, which it did. So we can test that we can put whatever graphics we want in the other playfield by moving some value to the start address of the buffer. And very faint, but we can modify the palette to make it more obvious. So now we have a new set of colors. These 7 colors, sorry. And if we set that to black, it will display more prominently. So that's our buffer. Now this buffer clearing business with the assembler can be deceiving because I'm going to remove my poke there. It can be deceiving because it conceals any errors. For example, a missing buffer clear routine, which we will make now, and we will just we will keep this very basic loop that we made a long time ago and make a slightly better one. So we want sky e minus sky. Want to divide that by, let's say, 8 bytes. The reason for which will become apparent shortly. I'm going to use D7 just because I am that way. I'm going to clear the 0 register and going to move that to A1 plus and make sure we actually clear 8 bytes each turn, and this will be a slightly more optimized but still CPU based clear loop. Obviously the best way, the best way, I don't know the best way, but the fastest way to clear a screen buffer is obviously to use the blitter and CPU together, but that's a little bit too advanced at this stage, I think. And the final thing we need to do is to do this. Make sure that the clear pointer is the pointer where we wanted to clear the screen is right there. I'm actually going to comment this out and show you something, really drive the point home about the assembler clearing the buffer for you. Want to fill sky to sky E. This is where the end pointer comes in handy. And we're going to fill it with some pattern. and start the demo, and this will display the pattern. So what happened there, if I assemble again, you will notice that if I don't fill it again after assembling, the assembler will have cleared that buffer for me. So the pattern is not displayed. So that's the way in which the assembler can conceal, omissions on your part, a missing screen clear routine at the start of the initialization of the demo. So I will end this tutorial here, and in the next tutorial I will start adding some bobs. See you then. Thanks for watching. Bye bye.